Swayam Prabha. Digital India. Educated India.
Let us now derive a mathematical condition with the help of which we can evaluate whether the object is going to float in a stable configuration or not. So as we have already seen, the point of buoyancy shifts to a new point. Let us call this point B prime. Now for small disturbances, it's going to shift orthogonal to the axis of symmetry. This particular thing is the axis of symmetry. This green line is the original water line and this blue is the water line. So the green thing is actually sort of showing us what the original configuration was. So the green line would have been the water line, and now you have shifted it, that is why it appears to be tilted. This is just for our reference. It does not actually exist. What actually exists is this blue line, which is the actual water line. Now let us say that into the plane the length is L, okay, and let us call this particular axis as X and this as Y. Now it has been tilted about the Y axis by an angle theta, meaning that this particular angle is theta. So if this angle is theta, this angle will also be theta. So let me just draw this. This will be theta. And correspondingly, this is also theta. Okay. This particular angle is also theta. Let me name the points. So let me call it A, O, B, C, D. Okay, so B has been repeated. Let me in fact call it as PQRS. So P, O, Q, R, S, T. So, and this is U, suppose, this particular point. So the new submerged volume is U, O, Q, S, T, U multiplied by the length into the paper. So now obviously the length into the paper is a function of X. It's not fixed, but it's to signify that yes, there is some kind of width into the plane. This can be actually a function of X. It can change because, like we discussed, it need not be a barge, it can be of a certain shape. So let us call it L for the time being. Let us not worry too much about L. Okay. So now let us try to find out what this particular shift is. So let us call this shift as X prime. So X prime happens, so the mathematical equation of X prime would be X prime multiplied by the submerged volume, that is the V of U, O, Q, S, T, U, and this is actually the integration of X times dV over the submerged volume, and integration of X, so about point O, the integration of X times dV is sort of this particular X multiplied by this particular area, right, into the length. Okay, and this, so this volume is essentially is integral X dA times L. This is going to be X dA times L. Now this dA in this part of the diagram will be something like this. It will not extend above the water line because it's part of the submerged volume. So let me quickly erase the areas for clarity. So now this is over entire V. So in fact, let us. This is going to be integral x times L times dA, and that area of integration would be over U O Q S T U. Now we can write this as integral x L dA over, so this particular area U O Q S T U can be written as P O R S T P plus ROQ minus POU. Basically, that symmetric area, that original waterline area, basically PORSTP plus ROQ, because that is the new submerged volume as we have already discussed, minus POU, because this volume has now come out of water. So let me call this as area 1, area 2 and area 3. So this can be written as this integral over area 1 plus integration x L dA over area 2 minus integral x L dA over area 3. Let us analyze the first integral. Integral x L dA over area 1, that is the symmetric part, PORSTP, that is PORSTP. Now PORSTP, that area A1 is symmetric about the y-axis, meaning that integration x dA, that integration x times dA for that particular area will vanish because it's a symmetric area. So this particular area is symmetric and hence this integral will vanish. So this becomes 0. Now what about the second and third integral? So let us write them down. So it is integral x L dA A2 minus integral x L dA A3, where A2 is ROQ and A3 is POU. Now to find out that particular area, let us see. So ROQ, so the area will be this element over here and x will be this. So it is integral of this x times this area. So this will be integral x times L times dA. So it will be, so this dA we can, this height, this particular height we can write in terms of x and theta. So what is, so dA will be dx, so this thickness is dx and the height is equal to, suppose we call it small h, and that height will be equal to x times, rather x upon tan theta. No, so wait, tan theta will be equal to h upon x. So yes, so the height is x times tan theta. So x times L times dA, well dA is going to be dx, that is this the width of this orange area, multiplied by x into tan theta. This you identify as the height. So dx times x tan theta is this particular shaded area, minus integration of xl dA over A3. Now A3 is this POQ. So again you can take a shaded area. The thickness of this shaded area is going to be dx, and the height of this shaded area from this axis is going to be again x tan theta. But now it is in the minus y direction because this is the x-axis and this is the y-axis. Now it is going below the x-axis, that meaning this particular height has to have a negative sign. This is above the x-axis and hence this was a positive thing, positive entity, but now this goes below the x-axis and hence it's negative, meaning it will be xl. Now dA will be dx multiplied by minus x tan theta because it goes below the x-axis. So it will be integration of x square dx L tan theta over A3. Now this minus sign comes out and becomes and combines with this minus sign, so it becomes integral x square dx L tan theta over A2. Okay, so essentially this becomes integral, or rather let me take out the L outside. It is going to be L, rather let me write it as tan theta times L times integral of x square dx. Now let us recall that the deformations are going to be small, and the meaning of a deformation going to be small means that the dx in the untilted coordinate system and the dx in the tilted coordinate system are going to be almost same, and for calculation purposes they can be considered to be same, meaning that the dx in this system and the dx in this, that is x in this system and x in this system, vary only by a small amount of tilt. And when we want to actually calculate this for the tilted system, it is much more convenient for us to do it for the non-tilted system, and thus we can write this expression as, so let me just move the images slightly to the bottom. So this expression for the so the left hand side was equal to x bar, that is the shifted location of B prime, the center of buoyancy, x prime times the volume submerged, let's call it V sub. This is going to be tan theta multiplied by L times integral x square dx. Now x square dx is the second moment of area about this particular origin. Now L times dx is going to be the area of the water line, because if I draw the top view of this, I repeat again, if I draw the top view, I am not drawing the top view to scale, but this is x, this is dx, and this is L. So L times dx is like the area of the water line, L times dx. So if I call this A, this is B, so this will be A, B, B prime, A prime. That is, from the top view, A, B, A prime, B prime is the water line, that is the perimeter of water that it makes with the floating object. Now L times dx is like dA of the water line, and thus this particular expression reduces to tan theta times x square dA of the water line. Thus x bar times V submerged is equal to tan theta times, so let's call integral x square dA as I naught, because this particular expression, mathematical expression, is tantamount to finding out the second moment, okay, over this entire area which is the water line. Okay, so it is this particular area that sort of is formed by joining the perimeter points of the water in contact with the floating object. So this is the second moment of the water line. So it is going to be x bar into V submerged is equal to tan theta times I naught. And for small disturbances, tan theta, rather actually we don't need to really invoke the small disturbance condition over here, because let us look what tan theta also is. This angle is theta, now this angle is theta. So from, let me call this M, because the vertical line joining B prime with the axis of symmetry is the metacenter. So this is M. So tan theta is also equal to BB prime, that is the shift in the center of buoyancy, divided by Bm. So we can go over here and say tan theta is equal to Bb prime upon Bm, and from this particular expression tan theta is also equal to x bar V submerged upon I naught. So from this we have, so Bb prime is like the shift in the center of buoyancy. So Bb prime is what we had defined as x bar. So this becomes x bar upon Bm is equal to x bar V submerged by I naught, and this yields Bm is equal to I naught upon V submerged. Now logically we can write down Bm, that is this particular line segment, as a logical break as Bg plus Gm, under the assumption that G lies between B and M. There is nothing sacrosanct about this, but it will help us in assessment. Meaning that if I split Bm as Bg plus Gm, meaning I am writing Bm, this line segment, as Bg plus Gm, I am assuming that G lies inside B and M. So if Gm comes out to be positive, means that G is actually inside Bm, and hence it will be a situation of a stable configuration. On the contrary, if we do this kind of breakup and we eventually arrive at a conclusion that Gm is negative, it means G lies above M, and hence that condition will become unstable. So it will ultimately boil down to us trying to find out just a small fact whether Gm is positive or Gm is negative. So Bm is Bg plus Gm, and this is equal to I naught upon V submerged, and this gives us an expression for Gm as I naught upon V submerged minus Bg. So now if Gm is positive, it means the configuration will be stable. If Gm comes out to be negative, the configuration is unstable. Now I naught is the second moment of area of the water line, and it is by definition integral x square dA. Hence I naught is always positive. V submerged is the submerged volume, it is also always positive, meaning this entity is always positive. So if Bg is negative, if Bg is negative, then Gm is always positive and the object is always stable. Okay. So ultimately, so this is like a special case where the point G does not lie above point B, but rather it lies below. Meaning, if we have an object, the point of buoyancy lies above this. So this particular configuration will always be stable. We can try to do some tilting of this kind of a shape, and you will see it's always stable. But in general, Bg is going to be positive, meaning G is going to lie above B, that is G is going to lie above B. So then Gm needs to be evaluated. Now depending on whether I naught upon V sub is larger than Bg, Gm will be positive or negative. Okay, so now it all depends on the shape of the hull and how much volume it actually submerges. Okay, so if we have a ship like this, and if the water line is over here, this is the water line. So let me attempt to draw the entire ship. It's not a very large ship. So the water line is going to look something like this. So this is the area of the water line. Everything below it is the submerged volume. And we're going to analyze the tilting about this particular axis. So let me draw it in red and across this axis. So we need to find out the second moment of area about this axis. So integral, so this will be x. Okay. So if I look at the top view of this area, so let me call it O, A. So this top, from the top, this area will look something like this. The red axis OA is this, and integral x squared dA of this particular waterline area will be what this will be. So we need to sort of increase I naught while keeping V sub constant, or we can reduce V sub also, but main point is you have to increase I naught. Okay, so the more I naught you have, the more stable it will be. So now you might have seen a kayak. This particular float is like an extension of the boat or a kayak, and this particular extension is called as an outrigger. If we take a typical shape of a kayak from the side, from the top, from the front view rather, it will look something like this. So this particular area into the plane would be like the waterline area, but they attach something like this. So it's basically another floating volume attached to the boat, and usually it's only attached to one side. So what is the logic of that? So first of all, this waterline area is now extra. So this waterline area, I'm not going to draw the top view again. So that waterline area is now at a distance which is significantly larger than any distance of the original waterline in the kayak. This floating object, okay, this is like the axis. I mean, that's not the axis. I mean, this is going to be the axis. So the boat is actually over here. So this is the boat. It's going to sort of rotate about this particular axis. Now, this is the moment arm for this second moment of area. Okay, so it's quite a large area. So the integral x square dA for this waterline of this floating body, basically this area, is going to be a very large number solely because x is large. So by attaching an outrigger, you give it a large I naught, you give it a large second moment of area, despite there nothing being in between. So the reason why nothing is there in between this is to reduce the viscous drag. So if you put a lot of floating volume over here, obviously if you put a lot of floating volume over here, you will get larger stability, but at the same time you will need a larger power to row your boat. So you avoid this, you keep the waterline small, but you keep it a larger distance. So by maintaining a larger distance, you have a larger stability of this object. But why is it kept only to one side? Now if this kayak is trying to tilt like this, the larger buoyancy of this float will try to restore it like this. So tilting in this direction is understood. But what about when it tilts on this side? So when it tilts on that side, the attachment, the outrigger tries to come out of the water. So it's something like this. So now it doesn't have any buoyancy force, and there is no outrigger on this side, but the sheer weight of this outrigger has a net moment. So if I draw the static diagram of this, the weight of the outrigger is something like this. So You're trying to tilt the boat in this direction, but the weight of the outrigger causes a moment in this direction trying to restore the entire object. So only one outrigger in any one side suffices. Okay, and this is why they attach outriggers. So they give a larger moment arm to the waterline, meaning while dA may not be a large number, the extension of the arm is such that it provides a large second moment of area which gives a large restoring moment, and the weight of the outrigger itself tries to restore the object when the tilting is in the opposite direction. Let me show you another outrigger. In this case it has a double outrigger just to drive home the concept. This is the axis about which this is going to be the axis about which we will analyze the perturbation to the entire object. So if I draw the front view of this entire object, it will be something like this. Now these are the outriggers. So from this axis, this particular outrigger is at a certain distance, maybe it's 2 meters or something like that. Look, the area of the outrigger is quite small, so the water line is just going to be the water line of these bamboo pieces. Okay, the water line area is quite small, but the x is quite large, so integral x square dA could be approximated as average location x. So let's say it's 2 meters square times the area of the bamboo. So the bamboo diameter is say 10 centimeters. So x square, rather this will be, I'll write down just an approximate value. This will be 2 square multiplied by pi into 0.1 square upon 4. This will be like the I naught for this particular surface. For this particular surface, the I naught will be differently calculated as per the water line of this particular ship. So let me try to draw the outline of the water line, whatever I can make out from the image. The outline of the water line is something like this, and similarly on the other side. So whatever that water line area will be, the second moment of that, and again there is a second outrigger over here. So they have not used just one outrigger because single outrigger is quite light in this particular case, and it will not give the restoring moment due to weight solely. So given a certain submerged volume, the way to increase the stability is to provide outrigger or to design a hull in such a way that the second moment of area is quite large compared to the submerged volume. Okay, if you can design a hull so that the second moment of the area is quite large compared to the submerged volume, then also you can achieve a large value of metacentric height. Large value of metacentric height will lead to a stable configuration. Let us consider an example of finding out the stability of a body. Let us consider that there is a barge. So a barge is like a ship which carries containers. It's mostly of a rectangular shape and there is stuff inside. So it is given that the barge has a uniform cross section and it has a width. So if we draw it from this particular view, it is given that the width is equal to 2L and the vertical height is h. So below the surface of the water, it is given that the height is equal to h. So the question is, what is the metacentric height? And the other question is, what is the range of the aspect ratio L by H for which the barge is stable? And it is also said that the G, that is the center of gravity, is at the waterline. Okay, so this is point G, point B is somewhere below. Okay, so let us start addressing the question. First of all, what is the V submerged? That is equal to 2L times the height times the width into the paper. So let's say the width into the paper is B. Obviously this is 2L, and if this is the level of the water, so this particular height is H. So this is the submerged volume. Next, what is the second moment of the waterline area? So obviously the waterline area, if you look at this waterline area from the top, it would have a length 2L and a length B. So the second moment of area about this particular axis is going to be 1 by 12 times B times 2L cubed. This is, we should be able to obtain this result fairly easily. So what is this? This is going to be 8 upon 12, which is going to be 2/3 BL cubed. So now we have the expression for mg, and that is equal to I naught upon V submerged minus GB. So GB is going to be h upon 2, because if the submerged height is h, and if it is given that G is at the water line, it's given that the G, the center of gravity, is at the water line. So obviously point B will be at the centroid of this submerged volume, and hence this distance and this distance equivalently will be h by 2. Therefore GB is h by 2. What is GB is h by 2. What is I naught upon V sub? This is going to be 2/3 BL cubed divided by 2L BH. So B cancels out, 2 cancels out, L square. So this becomes 2/3 L square upon, so 2 has cancelled out. So it should be 1 upon, it is 1/3 L square upon H. So this expression reduces to L square upon 3H minus GB. So GB is H by 2, which implies H upon 2 times 2L square upon 3H square minus 1. So this particular expression is this. So this implies that point G is this particular distance. So whatever this, let's say result 1 is, above point G. This is point M. So point M is this much distance above point G, and point G is at the waterline, and hence M is this distance above the waterline. And the condition for stability is that Gm greater than 0, essentially meaning 2L square upon 3H square minus 1 should be greater than 0, meaning L should be greater than square root of 3 upon 2H. So the length has to be larger than this. Only then this entire thing will be stable. Actually, we can write it in terms of 2L because the barge width is 2L. So 2L should be greater than square root of 6 times h. So the width of the ship should be larger than square root of 6 times the submerged height. This is the condition for the barge to float without any danger of overturning. Let us consider another problem in which we have a cylinder of specific gravity equal to rho. So this cylinder has specific gravity equal to rho, while the liquid is water and water has a specific gravity 1. So the question is, what is the condition of stability for this particular cylinder? So first of all, let us find out what the level of the water is. So determination of the water line. Now let's say the water line is somewhere over here. That is, it will have a cross section area something like this. So let this height be h. It is given that the length of the cylinder is equal to L. So the submerged volume will be pi r square multiplied by h. So the radius is equal to r. So this is the submerged volume. This multiplied by the density of water times g. So this is the force due to buoyancy. This is equal to the weight of the object, and the weight of the object will be pi r square L rho object times g. So now rho w can go over here, and this is equal to the specific gravity is given as rho. So this is rho pi r square L. Now pi r square cancels from both sides. This implies that h equal to rho times L. So if rho is less than 1, meaning the object is lighter than water, say like wood or plastic, in that case h will be a fraction of L, meaning h is less than L, and hence there is some part which is floating, and this is quite intuitive. So this is the first expression, and we will make use of this expression later on. So now we know that mg is I naught upon v sub minus gb. That is, this is under the assumption that the meta center is above the center of gravity. So now if we are able to find the condition where mg is positive, we should be able to find out the condition of stability. So first things first, let us find out I naught for this particular area. So from the top, it is this circle. So we want to find out, I call this x, and this is the dA. I want to find out what is integral x square dA. Now if I call this radius as, this is obviously the radius r, let me define an angle like this, theta. So this integral in terms of r and theta becomes, so x is r cos theta, so it becomes r square cos square theta. Now dA, so this particular length of segment over here, this will be rd theta. I need to project rd theta onto the x axis. Now if this angle is theta, right, then this angle is theta and this angle is theta. So if this particular length is r d theta, then this projection onto the x-axis is going to be r d theta sine theta. So dA will be this width, which is r d theta sine theta, multiplied by this entire distance. So half of that distance is r sine theta because it's the projection of r onto this axis. So it will be 2r sine theta. Essentially this becomes, so this is 2r to the power 4 integral cos square theta sine square theta d theta, where now theta will vary from 0 to pi. So this is 2r to the power 4. Let me divide everything by 4 and multiply by 4. So this will become 4 cos square theta sine square theta. So this integral 0 to pi sine square 2 theta d theta, which is nothing but r to the power 4 upon 2. I just simplified this as 1 minus cos 4 theta upon 2 integral 0 to pi. And because this function will vanish when we, so this integration will obviously yield a sine 4 theta, that will vanish, and this integration will simply give us pi. So essentially it's pi upon 2, and there is a r to the power 4 in the front, so it is r to the power 4 pi upon 4. And I mean, there are multiple ways of deriving this. I've just shown a quick way of deriving this. Moreover, what is the submerged volume? Submerged volume is equal to pi r to the power 2 multiplied by h. Essentially this is pi r square rho times L. So this is equal to V sub. So what is I naught upon V sub? It's going to be r pi r to the power 4 on pi r square rho L, and this becomes r square 1 upon r square by rho L. Now what is the height GB going to be? Oops, I think I missed out a 4 over here. So there should be a 4. This particular 4 I forgot to write over here. So this is 1/4. Okay. Alright. So what is GB? Now look, G and B. So this is something G, this is, let's say this point is B. So the distance between this will obviously will be equal to L upon 2 minus H upon 2. Okay. So now let us substitute everything in the expression for mg. So this is r to the power 2 divided by 4 rho L minus 1 upon 2 L minus H, and this becomes equal to r square upon 4 rho L minus, so now H is rho L, so L becomes common, this becomes 1 minus rho upon 2. So let us take L times 1 minus rho upon 2 outside, this becomes r square by 2 rho times 1 minus rho L square minus 1. So for this to be larger than 0, we have r square upon L square times 2 rho 1 minus rho minus 1 greater than 0. This implies r upon L greater than square root of 2 rho times 1 minus rho. So this gives us the aspect ratio of the cylinder. Now In fact, let us try to write it in terms of the diameter. So let us multiply by 2. So diameter upon length should be greater than, so if I have to get the diameter, I should multiply everything by 2. So this becomes 8 rho 1 minus rho. So the diameter should be flattish. I mean, let us put some value. So let rho equal to half. So d upon L should be greater than square root of 8. So rho is half and 1 minus rho is also half. So this implies that d upon L should be greater than square root of 2. So the diameter of the entire wooden cylinder should be 1.4 times the length of the cylinder. Means that the cylinder is a bit stocky in nature. That is, it's not as long. It's going to be something like this. And this also follows from intuition, because long slender cylinders will not be oriented like this. Rather, they will become flat. This is the condition for, this is the condition for the cylinder to float vertically up. Any other condition would lead to something else. It would become unstable. Let us consider another problem in which we have a cylinder which is lying flat on its axis. So basically it's something like this in water. Okay. So the question is, under what conditions is the cylinder going to be in a stable equilibrium? Is given that the specific gravity of this object is half. The specific gravity is half. So let us say that this is the water line, and first of all let's find how much of the cylinder is submerged. Well, because specific gravity is given as half, we can sort of say that half of it will be submerged, but it's a good idea to have a general expression for it. So in order to find the general expression, so let us find the general expression first, and then we'll find out the special case of specific gravity of the object equal to half. Okay, so let us call this height as h. So this height is h. Let this angle be theta. So we have to first find the submerged volume. The length of the cylinder is given as L. So the submerged volume is area submerged times the length. So area submerged is equal to, so the area of this right angle triangle, it will be, so if this radius is r, so the area will be half of height into this length, let me call it as small l, times 2, because there are two such triangles, and this is actually height times length, and this is actually, so the height in terms of of r and theta will be, height is r cos theta and length is r sin theta. So this is r square upon 2 sin 2 theta. But this is not the submerged area, rather this is the area of this particular sector. Not the sector, this particular triangle. Now we have to also add, if I call this OPQ. So this is triangle OPQ. Now the sector PQ measured in this direction, that particular area will be, so this angle as per our convention is 2 theta. So this angle is 2 theta. So this particular sector will be 2 pi minus 2 theta upon 2 pi times pi r square. So the total area, this A submerged, will be r square upon 2 sin 2 theta plus, so this is 1 minus theta upon pi times pi r square. So this is the area submerged. So the volume submerged will be equal to r square upon 2 sine 2 theta plus 1 minus theta upon pi times pi r square multiplied by length. So now the force due to buoyancy will be this multiplied by the density of water. So basically r square upon 2 sine 2 theta plus 1 minus theta upon pi r square L times rho water, and this will be equal to the total volume. So pi r square L times the density of the object. Now rho water upon density of the object becomes the specific gravity. So I can write it down as Sg. L cancels out from both sides, that's fine. And let us divide everything by r square. So r square cancels out. So and let us divide everything by pi as well. So it becomes sine 2 theta by 2 pi plus 1 minus theta upon pi is equal to Sg. So this equation is a transcendental equation in theta. And we must solve this equation to find out the value of theta. So in case Sg, the specific gravity is half, so we have sine 2 theta by 2 pi plus 1 minus theta upon pi is equal to half. And let us see by inspection, let us put theta equal to pi by 2. So this particular term becomes sine pi and this particular term vanishes. This becomes 1 minus, so on the this particular term is half, and this is actually equal to half, which is also the RHS, and thus theta equal to pi by 2. So 2 theta, which is the angle, it becomes pi. So from this little exercise we conclude that half of the cylinder is actually submerged. This is the cylinder, then half of it is submerged. So this is the water line. Now the condition for stability. So what is I naught upon V submerged? Now V submerged is simply pi r square upon 2 times L, that is half of the cylinder. This particular volume is submerged, and I naught is, so despite the cross section being a circle, the water line is going to be a rectangular one. So if I draw the top view of this, it will be simply this, where this is the length of the cylinder and this is 2r. It does not depend on the cross section because we are looking at it from the top, so a cylinder will look like a rectangle, and I think you have done this in engineering drawing. So I naught will be 1/12 of L times 2r cubed, and this is 8 by 12, so this is 2 by 3 Lr cube. Alright, so I naught upon V sub reduces to 2/3 Lr cube divided by pi r square upon 2L. So L cancels out, and this becomes 4r upon 3 pi. So now mg is I naught upon V sub minus gb. So in order to find out gb, so we know that the center of mass is going to be at the water line, but what is the position of B? So in order to find the position of B, it is quite easy. You just have to find the center of volume of half of this volume, and I leave it as an exercise to show that GB comes out to be 4r upon 3 pi. So this is a very straightforward exercise, and I think you might have done something like this in class 11 and 12, if not in your first year. So With the help of this, we finally obtain that mg, so v I naught upon v sub 4r by 3 pi minus 4r by 3 pi, and this becomes 0. So it means that in this direction there is no sort of issue of stability. It's going to be neutrally stable, and this we know that if we roll a log along the surface of the water, nothing happens. So basically this calculation, whatever we did, was along sort of tilting in this angle. So this was the second moment of area. So this result prompts us that we should try to find out what happens when you tilt this along this axis. That is, when you try to tilt it like this instead of this. Okay, so you're tilting it along this axis. So the water line second moment will be along this direction. So x square dA will be this. So if this is x, then this is dA. So in that case, I naught will be 1/12. Now if this is that integration direction, this will be L cubed times 2R. And this divided by the submerged volume. So submerged volume remains unchanged, and that submerged volume is pi r square upon 2L. Alright, so this becomes, so this 2 goes on top, so this becomes 4. So this is 1 by 3 pi L square upon R. So about this axis, it is 1 by 3 pi L square upon R. And the height, the height of the point of buoyancy is still going to be equal to this. That is, this distance is same in this view also. Okay, it will be somewhere over here. So this distance is 4r upon 3 pi. So mg in this particular axis of tilting, okay, this will be 1 over 3 pi L square upon r minus 4r upon 3 pi. This has to be greater than 0, and this implies, so 3 pi gets cancelled, so to say, and this gives L square greater than 4r square, that is L should be larger than 2r. So unless L is larger than 2r, tilting along this will become unstable. That is, if length is less than twice the radius, then this configuration will not be stable, but it will become something like this. Okay, it will start to float something like this. And the other obvious result that we have just obtained is tilting along this axis is neutrally stable. So this is neutrally stable. There is no net moment causing it to become unstable or restoring. And it is obvious because this entire shape is sort of axisymmetric about rotation. So if I mark this point as A, even if I rotate this, point A will come here, but the water line and the submerged volume will still remain the same. So this is sort of neutrally stable along this axis. But along this axis, we have analyzed and found out a condition for stability. So with this, we conclude our analysis of fluid statics for floating bodies. And we have seen how the second moment of area contributes towards the stability of floating objects. So it's goodbye from me. Bye.